How is it going? We are going to be covering today. This is 7.3 in the book. However, I don't like to look at that because I give out guided notes and I don't give out the book anymore. This is Unit 7, Day 5, and I'm breaking this up into two parts. This is Part 1. Okay, there's a separate lesson for Part 2. Okay, today we're going to work on volumes. All right, volumes, and do some integration today, kids. So let's jump right into it, and let's go. All right. Find the volume of a pyramid. Now, obviously, we can use geometry for these perfect shapes. Not everything we do in calculus is going to be a perfect shape. In fact, when we have to find the volume of things, chances are they will not be perfect shapes. So we're going to have to use integration. But let's use integration and come up with an answer that we know what it should be. Okay? So the volume of a pyramid, which should be to no shock of anyone here, is 1/3 length times width times height. If we wanted to, because a pyramid is like a third of a cube, okay, notice length times width times height, they're all the same number. I could really say that's 1/3 s cubed. Okay, you can do that same way, or 1/3 s cubed. All right, so shocker. Let's figure out what the volume of this cube is. Or I'm sorry, this pyramid is. Well, I have 1/3 times 3 cubed, which is 1/3 of 27, which is 9. Okay, 27 divided by 3 is 9. The volume of this pyramid is 9. So if we were going to use integral calculus or integration or antiderivatives to figure out this volume of this particular pyramid, we should get 9. Okay, no arguments from me right there. All right, so let's complicate this a little bit. Okay, let's find the volume of the pyramid. Consider a horizontal slice through the pyramid. That's this thing right here, down here with this green line. This is a horizontal slice. Boom, right there. Okay, if I take a horizontal slice out, okay, the volume of the slice is s squared times dh. How is that possible? Yep, there goes my marker. Well, it's possible if I were to make this slice in this 3D shape, maybe it was right here, it would go across to this side, come up to this side, go back across to this side, come down. That, my friends, is a square. Okay, that's a 2D shape. However, when I add thickness to it, so let's say it comes down a little bit. Now it's a 3D shape, all right? And the thickness, okay, the thickness of this slice is DH, okay? And then let's call this S for side, okay? So for the volume of anything, I find the area and I multiply it times its height. Okay, I take the area of this top and I multiply it times its height, which is this distance here. Length times width times height, so to speak. All right, so I can take my side, okay, S. This side is also S. That's where I get my side squared. And this thickness is a small change. It's the same one down here. It's such a small change in height, we are going to make it insignificant, just dh. Because when we integrate, right, we have a dummy variable. That's going to be our height. All right? So if we put a 0 at the top of this pyramid and make down the positive direction, meaning 0 is right here, and then I go down 3, okay? If I go down 3, then S equals H. What does that mean? Okay, and really this is, I mean, it's good to understand the problem to cover this, but if you were really solving this problem, we wouldn't need these in-depth detail and information. However, okay, notice that this base is 3 and this height is 3. Remember, it's perfect, the dimensions, just like a cube is. So whatever this dimension is, we're going to call it S, is the same thing as this dimension, the height, S. All right? That's all that's saying. So if I do that, okay, if I make S equal to H, S is equal to H, all right, then the slice, the volume of the slice is now H squared dH. All I did was take the, highlighter. I took this S, and since S is equal to H, I just changed it to an H. So instead of saying S squared dH, it's now H squared dH. All right? So if you remember what integration does, integration really adds up. I remember when we started to learn integration, we did the area under the curve. We made a whole bunch of rectangles, and we added up all the areas of those rectangles with LRAM and RRAM, because that was really on our way to integrating. Okay? So integration adds up a series of values. So what do I want to add up? Well, I want to add up, if I want the volume, I'm going to have this area of this rectangle, the area of this rectangle, the area of this, and I want to add up all these areas. Okay? And that's going to give me the volume. So wouldn't it make sense that if I want to add up a series of things, I integrate? And I'm going to integrate the areas. Okay? Isn't the area of a square just side squared? Okay? The area of our slice, without considering if this was a perfect square, the area of this is side squared, right? Area equals side squared. I want to make it a volume, then I multiply it times its height, okay? And remember, instead of S, we're going to call that H. All right, so this is the area, H squared. And we are going to integrate that. dH becomes a dummy variable that we don't use anymore. So I take whatever the area is, H squared. I put the dummy variable here, and I integrate it. That's all we do. Anytime we want to find the volume of a shape, I take the area and I integrate it. All right? That's the big takeaway. Okay? Anytime I take the volume of an area, volume of a shape, I should say, I get a cross section and I find out what that area is, and I just integrate the area. Volume means you integrate the area. Okay, I've said that enough time to confuse you now. So let's go ahead and find out the volume of our pyramid, which should be 9, right? Well, this is a simple integration. If I integrate this, it's going to become H cubed. I add 1 to the exponent and divide by that. Oh, by the way, I want that from 3 to 0, which means I get 3 cubed over 3 minus 0 cubed over 3. Love when I get to plug in zeros, because zeros just go bye-bye. 3 cubed is 27 over 3, and oh, by the way, that's 9. Okay? So integration works, especially when we don't have these sweet, sweet, easy shapes. We find the volume by integrating the area of the cross-section. Okay? Let's take a look. Okay, a method of slicing. And this is called slicing. Well, I think you guys have guessed it, because we really just take a slice from the inside of our shape. In this case, our slice happens to be a square. The area of a square is side squared. So we integrate side squared. That's it. Okay, so it's called slicing. Again, I'm not using the book anymore. I mean, the material in the book and the pacing is by the book, but I don't actually have the book in hands of students. So let's sketch the solid and a typical cross-section of that solid. All right. I mean, you don't always have to do that. Sometimes it's just given to you, but you can. I like drawing 3D shapes. Okay, now we need to find an equation for volume. Now, remember, not remember, I want you to remember. That means you're going to extra remember something. That volume is just the integration of the area. Volume is just the integration of whatever the area is. Okay? Well, if we want a number and just not an equation when we integrate, we're going to need some bounds or some limits. We're going to need a lower limit and an upper limit. And then let's just do the math and integrate it. Okay, that's really it. So when I'm finding the big thing here is when you're finding the equation for the volume, your volume is, okay? Let's remember what math means. Volume is means equal the integration of the area, okay? Visca. Oh my goodness. I see, said the blind man, and it spells Visca. Goodness. Visca the teacher, follow me on YouTube. Ring a ding ding, ring that bell. Now, Cavalieris, I'm Italian. In case you didn't realize, my last name ends in a vowel. That's not always the case for being Italian, but happens to be common. Okay? And Mr. Cavalieri, I'm assuming he's Italian. I could be wrong. Who knows? I'm going to claim him anyways. So, two solids with equal altitudes and identical parallel cross sections have the same, wait for it, volume. Okay, so if I have this tube, this cylinder on the left, okay, that would have the same volume as the right. How come? Because it has the same altitude, which means they're both have the same height, okay, and they're cross sections, they're parallel cross sections. Parallel means at this height, these things are identical. Okay, I mean, it says identical cross section right here. So it's fun when you got like some sort of clip art that you're putting on there. But what's better is Cavalieri say, click a me, click a me. Yeah, he sounds like Mario. That's right. He sounds like Mario. I heard he also did some plumbing. Anyways, we've all done this as a child. We've all stacked some coins. I don't know, maybe you guys haven't. Yeah, smartphones nowadays, maybe virtually stack coins, who knows. But you stack coins. Let's say there's, I don't know, 24 coins there. And there's 24 coins here. I mean, I know for a fact, you take your finger, and 1, 2, 3 fingers below that, and a thumb, and you push here. And you push this to the side so it starts bowing out like this, almost to the point where it almost tips over but doesn't, and you get something that looks like this. This volume is the same as this volume. If I take the surface area, if I take the area of all these coins and add them times 24, if there's 24 coins, there's still 24 coins here, and the area is still the same. There's going to be the same volume. It doesn't matter the shape. Okay? If they have the same height, they're both a height of 24. Okay, and that cross section is the same. The coin here, I mean, they're the same coins, then it's going to be the same volume. That makes common sense, but Cavalieri, that was like a major contribution to geometry and ultimately to calculus. All right, let's go. Let's do this poop. The cross sections are squares with bases in the XY plane. All right, not a lot they give us, and more so the information that we're going to use to solve this is actually in the drawing itself, okay? So, here we go. I want to find the area of this image that they give us, all right? And I'm looking, and I see here's the X, the Y-axis. This is the vertical, or yes, the vertical Y-axis here. I know it's kind of tilted at an angle. Okay, here's the X-axis. And on this set of axes that they give us is the graph, do this in blue, y equals x, x equals y squared. So come around like this, hit the top, come back, come up here. Okay, and the cross sections, meaning the image that goes from here to here, the cross section, they're squares. Okay, then the next one, we'll do this in different colors just so we have a little better visual. The next one comes up like this, comes in front. Oh, look at our drawings. They're so pretty. Pretty drawings. You're such a good drawer. Thank you. Okay, there we go. All right. So, okay, if I need the volume of this, I'm just going to, okay, volume is the integration of area, and the area is side squared times d, the dummy variable, use the same variable, and I need bounds and whatever. But here's the kick. What in God's tarnation is the value of that side? Oh, by the way, my bounds go from, in case you couldn't tell, I'll do this in, let's do this in orange. When x equals 0 to when x equals 4. Okay, so we got from 0 to 4. All right, not too bad. Can I just throw y squared in here? Because look, I got x equals y squared. No, I cannot. How come? These are x values. Okay, if my bounds are x values, I want my dummy variable to be an x, and I also want x variables in here. Yeah, I'll be okay. I'll put the e at the end of variables. Well, the second last letter. I'll be okay. I teach math, kids. My math is correct so far. So I want, if my bounds are x's, my dummy variable needs to be an x. That means I can't put y squared here. So if x equals y squared, let's solve it for y in terms of x. Okay, what do I mean? That means the square root of x equals y. Okay, and that's what I'm going to put here because I don't want y squared here. I don't want the integration from 0 to 4 of y squared dx. That's not good. This should have an x as well. So I'm going to solve for y in terms of x. Now that's good, because don't forget, these are in x's. So everything should be in x's in front of your face. All right, that's a simple integration. We'll do the integration out, and then we'll check it on the calculator to make sure our work is accurate and correct. All right, so I'm going to change this to say x to the 1/2, because integrating with exponents is a million times easier, and it's how it should be done. So I'm going to add 1 to a half to make it 1/2. That's 3/2. Then I divide by 3/2, which is the same thing as multiplying by 2/3. All right? And I want that from 4 to 0. Glory be, I get to put a 0 in again. So I've got 2/3 times 4 to the 3/2 minus, and I'm going to put a 0 in there. And I love zeros when they make everything go bye-bye. Okay? 0. Bye-bye. So I really got to just evaluate this. Okay? This tells me the root. The square root of 4 is 2. 2 cubed is 8. So I've got 2 times 8. 3. That's 16/3. That goes in 5 times 5 1/3. Or you could write it 5.333 with a line over it. The AP Calc exam normally always goes 3 decimal places. This is exact. Okay? I mean, that's not how we write exact because we really don't use lines over it. But 5.333 with a line or that would be acceptable. Okay? So let's see if we did this right. Let's see if we did this right. Okay? Let's get out our handy-dandy calculadora. Let's take a look at the detached screen because I know sometimes you guys are not always on computers or laptops or Chromebooks or Macs, or sometimes your smart TV can do these things. I do it at home on my Fire TV. I love it. But sometimes you're on a phone. Okay, so we need to, if you're on a phone with a smaller screen, I'm going to blow this up for you. And I'm going to put in what I had here in blue before I changed it to x to the 1/2. I'm going to use the square root of x. So in case you forgot, math number 9 is where I do my integration from 0 to 4 of the square root of x dx. Yep, I should get dx. Okay, and I should get 5.33333. And remember, the calculator does integration slightly different, so it might be off after about 6, 7 decimal places. Okay, but that would be what we're looking for. And there it is. And look at, oh, look at that. 1 2, 3, 4, 5, 6. The 7th decimal place it's off. So this, if we rounded it 3 places anyways, is what we would get. And that is spot on for what we want. Put us here. We came up with that 5.333. Good, 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 good. I like it. You guys are good. You're good people. You listen. And that's what you get when you listen. You get to be smarter. All right. Let's do another one. I'm going to roll. In fact, we only have one more to do. This is going to be a nice, it's going to be under 30 minutes. And we're going to be good. Okay, this is actually off the 2012 AP Calc AB exam. Man, 10 years ago, because I'm doing this in, this is January 13th of 2022. Woo! All right, so this is part 1B, okay? So you have multiple choice where you don't use a calculator. They don't allow it. It's like the SAT, okay? There's sections of the test that you use a calculator, and there's sections of the test where you don't. There's multiple choice where you use the calculator. There's some multiple choice where you don't. There's some short answer problems that you can use a calculator. And there's some short answer problems where you don't use a calculator. This happened to come off of a multiple choice section where you get to use the calculator. How do I know that? The number is 92. There is not 92 or 100 questions. Don't get me started on the numbering convention for the AP Calculus exam. The first set of multiple choice is like 1 through 24. Then the next set of multiple choice is weird. It goes from like 78 to 93. It's crazy. Those numbers aren't exact, but it skips numbers. Okay, so don't freak out. Another reason I know that you get to use a calculator is most of the problems that have multiple choice selections like we have here, they're all 3 decimal places. You're going to have to use a calculator for. You could come up with this 3/10, or this 1/3, or this 7/10. Those are easy. But you're not going to come up with something like this or this with paper and pencil. Okay? So we get to use a calculator here. So, oh, we get to draw. I love drawing these graphics. So problem 92 on the 2012 AP Calculus AB College exam states, let R be the region in the first quadrant bounded below by the graph of y equals x squared and above by the graph of y equals a square root of r. Capital R, which is the region, not the reason, is the base of a solid whose cross sections are perpendicular to the x-axis, and they are squares. What is the volume of the solid? So I know I'm actually going to integrate squares because that's what my cross section is. Okay, so in my mind, okay, I'm going to integrate the side squared because that's the area of a square, and then times a dummy variable, and I need some bounds. Okay, that's going to be my volume. Okay, I'm going to put that in the calculator at some point. I just got to figure out what's what. So I'm going to graph this. Okay, I'm going to graph this, and I could graph it in the calculator to show you. Oh, yeah, why not? Let's be precise. Okay, so it's going to be x squared and the square root of x. Clear. Let's go to y, and I'm going to blow this up onto the slide in a minute. So, well, why not? You guys are here. You're committed at this point, so let's just do it. All right, so x squared and the square root of x. Now, if I graph these two things right now, here's x squared, and here's the square root of x. These things only cross or touch at 2 points, at the origin and right here at 1, 1. So I'm going to zoom into that area so we get a better view of it, okay? And besides, it tells us in the problem, the region in the first quadrant. So I don't care about any other quadrant, okay? So let's do a zoom. Let's zoom a box because I could draw this bad boy. I'm going to hit enter. Up here, oh, there's the one side. Go above the 1, then go to the right of 1 on the x, and hit enter. So I'm going to zoom in here. Oh, that's pretty. I would have drawn it better, you know. Maybe not as precise, but it would have been better. That's just personal, you know, my personal feelings here. Okay, so if you had to sketch this, okay. We draw the y-axis. We draw the x-axis. Here's 1 on the x. Here's 1 on the y. They intersect at that point. They also intersect at the origin. Okay? So let's do some yellow here. They intersect here at 1, and they intersect at the origin, which is 0. Those are my bounds. Okay? So here is the square root of x. Here is x squared. Okay, I guess I should say y equals. All right, and the cross sections are squares, and they are perpendicular. So obviously, perpendicular to the x-axis is like that. It would be parallel to the y-axis. So I'm going to draw all these squares. It touches here, comes down to here, and it makes a square. Touches here, square. Here, and you're going to have a whole ton of them. And the closer you get to the end, the smaller your squares are going to be. Okay? So you have a bunch of squares. So the question is side squared. The area of a square is side squared. So I need to figure out, purple, what is the length of the side? How do I calculate that? Okay? I calculate that by taking the value, and I'm going to do this, let's do this in orange. The value for this first square that I drew on the leftmost, right here, where the S is next to it. I take whatever the value of this is, and I subtract whatever the value of this is. So look, I take whatever x value is right here. I don't know it. I take the square root of x, because that's this point, and I subtract x squared, which is that point. And that's the length of this side. So my side, for every square, even the square right here, let's do this one. Whatever x value this is here, I'll do this in a different color. Let's go purple. Whatever this x value is right here, I take the square root of that x value here, and right here I just square that, and I just subtract them, and that gives me this distance. Okay, so for every square, my side is the square root of that x minus squaring that x. This is going in for my side. Okay, so volume is the integration of square root of x minus x squared dx, because we're going to use x's now, my bounds from 0 to 1. And let's just put that in the calculator and hit enter. Okay, let's put that in the calculator and hit enter. Oh, I love putting this stuff in the calculator. So let's integrate again, math 9, from 0 to 1. And I'm going to take the square root of x and subtract x squared. Remember, dx, our dummy variable, that is our side. Okay, that is our side. And I hit enter. And it gives me something funky. Why do I feel like I made a boo-boo somewhere along the side? Oh, I caught it. This is my side, right? That's S. Doesn't area mean I have to square the side? Haha. If this whole thing is a side, I gotta square it. And look, this is a really good teachable moment. I'm looking at this, I'm like, that doesn't seem right. Such a small area. But anyways, teachable moment. You see what I did here? All I did was forgot to put the square right here. And look at the answer it gave me. It gave me a valid answer, C. So when they make these calculus exams, they figure on a mistake you might make, and they put that there. Okay, so let's just redo this whole thing. Well, I'm just going to come up here and hit enter. And let me insert, oh, I got to do parentheses. Look at me go. Second, insert parenthesis, parenthesis, squared. There it is. That's it. Okay, there it is. So I'm going to take this, put this over here. All right. You need to have your side, and your side is squared, because the area of a rectangle is side squared. Was missing that here, and look, it looks like it should be this choice, but it is definitely, if I round 3 places, that 8 goes up to a 9. Bam. There you go. Wow. Whew, good catch. Good catch. I mean, I don't know, maybe you caught it. Maybe when I was doing this, it's like, Visca, you forgot the 2, the square. Maybe. But you got to be able to catch that stuff. That shows a sign of intelligence. So if you caught it, you are intelligent. And if you didn't, you're just watching this, and you know, you're still smart. You're in AP Calculus. Don't put yourself down. I make mistakes too, obviously. You see. But you got to catch them. You got to catch them. All right. We are done. And 30 minutes on the button. Pretty solid. I'll see you later.